Right, our next speaker is Payal Das, who is a principal staff member and manager at IBM Research. And in the foundation models community, she was involved with the Moleformer, which was one of the first more than hello world examples in that field. And I believe she flew in from Central America in the middle of another meeting.
San Juan.
San Juan.
Yeah.
Okay. But regardless, thank you very much for your very short trip and very happy to hear your talk.
On now, right? Okay, awesome. Yeah, good morning again, and I would like to thank the organizers first to allow me to come here and share some of our side of the story. I'll talk about my title of my talk, and this is the first time I'm gonna give some of this talk, so bear with me if I humble and so the title is Next Generation Frameworks of AI, Science and Trust, a Memorization Perspective, and this last bit is a little bit new, and I hope I can convey the message. But let me tell a bit about who we are, what we do. We are from the Trustworthy AI research team at IBM, and we have been working for several years on trustworthiness of machine learning models, starting with explainability, robustness, and so on and so forth. And over the last, I would say from 2015 and onwards, we have been working on foundations of generative AI. And we look into different applications, like establishing generative AI for trust, for science and business. And we also have been working on AI for good. And some of our exposure or some of our demonstration on our generative AI algorithms and foundation AI algorithms in this space of accelerating scientific discovery was to fit that umbrella of work we have been doing on AI for good. And I just wanted to share a few where since we are in industry, we don't have access to immediate labs. So whenever we have to do validation or we have to work with collaborators. So over the years, we have been lucky to have wonderful collaborators, either from industry or from academia, who have allowed us to run some of this verification. And this slide is to show some of our earlier work. This was not transformer-based architectures, but still working in the paradigm of foundation model where they were trained on broad data at scale, and then were further fine-tuned for a downstream task adaptation scenario. On the left, you see that the model was able to, the generative AI model in this case was able to discover new antibiotics, and on the right, the application considered was designing inhibitor for different SARS-CoV-2 targets. And in both scenarios, this was also a learning lesson for us that for antimicrobials, we were able to design out of 20 synthesized and tested candidates, we were able to find 5 antimicrobials, but 2 that were showing high broad spectrum potency, low toxicity, and low resistance onset. And for the COVID inhibitor, we did find 4, 2 for SARS-CoV-2 spike and 2 for main protease, and one of them, interestingly, showed broad spectrum potency all the way from Wuhan to Omicron. And we did see when you work with the collaborator that it is indeed the case. If you bring such AI architectures in the loop, it does help to narrow down your space of hypothesis and run a small number of experiments. And likely, hopefully, the success rate is high enough. And since Moleformer was already mentioned and already introduced, I believe, to this audience, I won't go into much details. I would, but from a different perspective. But we have been also running this server where we provide access to Moleformer for inference and some of the generative architectures. So go try it out if you are interested to see, to run some predictions there. And with that, we also have added the Moleformer model. Again, bear with me if you don't know what is Moleformer. I'll tell about that in a bit. But the model, we have a model trained on small fraction of data already in Hugging Face. And as of yesterday, it has over 1 million download. And I don't know, who is using this model. But hopefully, during the tutorial yesterday, this was used. And maybe, that's what created a number of downloads there. And the one last thing I want to mention in this slide, we are working with Moderna, who is one of our collaborator, and we are subjecting some of what we have learned to help them design better RNA vaccine stabilizer, which is going, in my opinion, amazing. So the perspective I want to bring in today's talk, slightly deviating from actual Molformer, how it was built and all, is that, why we have been hearing from different speakers in this topic, the symposium is about scientific foundation model, that why do this sound foundation model work? And of course, that we know that they work because they are big, they are trained on data at scale. But more from mechanistic perspective, recently over the last few years, and this is being established more and more, particularly in the context of language models, that the reason they learn, because they learn to memorize. So they look for certain pattern, could be a fact, could be a writing style, could be verbatim text, and that is all what it remembers, and then it finds some short part or shortest circuit and output those what it has memorized during generation. And that seems to be like, at least, one common mechanism across different tasks, across different scenario, that memorization at least holds, some of the success key for foundation model. And this is a beautiful, overview or survey on memorization by Hartman. They have also provided a taxonomy, and as you can expect, that memorization do help in certain case. For example, generalization in QA task, or for style transfer task, and or making the model aligned, and so on and so forth. But of course, if we remember too much, and all what we do is remembering, then there is also risk. And that is what we have been seeing a lot, I think, in the last few months, that models that are built on large-scale public data, they are at risk of absorbing copyrighted material, or at risk of outputting private information like email and things like that. And this is becoming a common trend. So there is a lot of research ongoing on the mechanistic aspect, that how memorization happens, but also empirically testing, has memorization happened, and if it has happened, then what could be the risk, or what could be the positive aspect of it. And these are some key works that I find really interesting. I think Carlini was one of the very first one who, in the context of a large language model, did show by using a training data extraction attack that LMs indeed, they tend to memorize and regenerate segments of the training data. And more people started looking into it. And of course, as you can expect, the duplicated training data, because we talked about training at broad data scale, no filtering, no curation, etc. And initially, even like when we started working on Molformer, that was, I would say that was probably 2-3 years back, that it was the notion that let's train on everything that exists on web, and we'll get a model that is as powerful as possible. And that stayed for a while, but then when we started looking into how it works and why it is being successful, like the Kanpal and Lee, they looked into it, and they found that duplicated training data is one key factor of memorization, and of course deduplication can effectively reduce. But it was not just duplicated training data, it was more than that. Model scale is another factor, the context length has been found to be another factor, and there are many other probably aspects that we haven't looked at yet into it. And last but not the least, though it may sound like I'm trying to criticize here memorization in a foundation model or language model specifically, it seems that it helps. That if you know certain facts, certain knowledge, certain style, it helps the model to generalize, and it has been proven again and again that memorization and generalization ability of foundation models, these two are actually related to each other. So with that, I plan to cover these two questions in this talk, that does memorization play a role in scientific foundation models? And we take our own Molformer as a case study to see that if it indeed happened, and more in a retrospective manner. And then in the last bit of my talk, I would try to cover a new architecture we are coming up to augment language model with an adaptable external memory. And with that, the question we are asking that, how can we control language model through test time memorization? Because all if it knows is about memorizing training data, and let's say that if the training data is wrong, or is non-factual, or is private, how we can control it the language model in test time by building a new memory, or by associating with another memory which will act as a controller during generation or during inference. So that's like the construct of today's talk. So I'll do a quick introduction of Molformer now, given that I have spoken enough about it without telling what it is. Molformer is a foundational transformer for chemical small molecules, and it has been trained on the largest to date in our lab, which we have trained it on 1.1 billion chemical smiles from PubChem and Zinc. And Venkat yesterday told me that they have now a version of Molformer or similar that is now trained on 2 billion smiles, so very good. And on top of being trained at over 1 billion chemical smiles, because though we come from industry lab, we don't have unlimited GPUs, we added linear attention, which is an efficient version of the vanilla attention and gives linear time complexity instead of quadratic complexity. And to model the position, the interdependence of the tokens within chemical smiles, we used relative position and embedding as opposed to absolute position encoding, which is used in vanilla transformer. So with these two and tricks for training it at a distributed manner, like adaptive bucketing, which is conditioned on the variable length of the token of the strings, we trained the model, and so far we have tested the model in more than, I would say, 70 plus property prediction tasks. This is an encoder-only model. And also we have found that there is some behavior, let's call it quote-unquote emergent behavior, that there seems to be learning of some geometrical features or taste or odor of the molecules without having access to the information. The paper was published again 2 years back in Nature Machine Intelligence. So if you are curious, you can find it, or I'll be happy to talk more about it. And some performance of Molformer, of course, we have benchmarked is across GNNs, graph neural nets, and language models. And this is a glimpse where we have subjected it to atomization energy regression task in QM9. And a reviewer asked us to compare with SNET and DimeNet. SNET is a GNN which use a continuous convolution, and DimeNet, I think, use a particular message passing mechanism. And those are very sophisticated architecture and very specialized architecture for handling QM9 and similar tasks. So the point that we wanted to make here that, of course, Molformer is an order or two order behind of SNET or DimeNet, but it's more general. So if you just take any model, and in this case the model was first trained on 1.1 billion smiles, and then were fine-tuned on this QM9 task regressed values. So you can see that while it is some order, 1 or 2 orders behind of SNET and DimeNet, which are specifically designed to handle QM9 tasks, the model maintains its generality when you look into physical property prediction tasks from MoleculeNet, and that we have seen across the board. And these are more benchmarking now on classification task from MoleculeNet. And you could see that, again, one model acts as a general foundation across different property prediction, classification, and regression tasks. So, but what was interesting is that when we were looking into the scaling behavior of Molformer as an ablation study, we found that that if we take, instead of 1.1 billion, if you train it on a 100 million subset of that original training set, the model starts to perform poorly across different tasks. Also, if we keep the data scale as it is, if we consider a model that only has half of the parameter as Molformer XL, which has 12 layers and 12 attention head per layer, and so the Molformer base is that baseline, which is half of Molformer XL size. Again, that there also we see consistent performance degrade across different tasks. And all of this now is trying to tell us that now that we look into these results retrospectively, that was memorization indeed happening in learning of Molformer XL, and that is why it is so successful, because it has learned to recognize some general patterns. And indeed, because we take raw dump from PubChem and Zinc, the training set indeed contains a lot of duplicates, which actually also reflect the bias in scientific databases, because some of these molecules are just very popular, or some of the molecules are popular because there is rational choice, because the molecule is useful in more than one application, or is easy to synthesize, and so on and so forth. And this is reported that in scientific databases, what we see is not a true representation of molecules, rather it's, there is a lot of anthropogenic bias and rational bias reflected in the curation of those databases. And last but not the least, if you look at the graph on the plot at the bottom, this shows on QM9 prediction task how the mean absolute error changes as we train the model, pre-train the model on different fraction of data. And this is interesting to see that for some measures, you don't need to see all of the training data. But for some, clearly, you could see that it needs to see 100% of the data and maybe can benefit from even more because they may still not very close to zero. And all of that is, again, indicating that the likely Mole-Former Excel is successful, at least one factor being that it has learned to memorize through the number of parameters it has been dedicated to and also through the exposure to this training data. And and we continue the journey, and this should be shown, the preprint would be released, where we continue to explore this angle, but now from the generative aspect. So we call it this model GP Mole-Former, which is built on top of the Mole-Former-based architecture, but now trained in a GPT-like manner for generative tasks. So it's a causal language modeling objective instead of mask language modeling, which was used for Mole-Former. But still trained on the same one over a billion molecular smiles, and we subject it to different tasks like scaffold condition generation or property condition generation, as well as de novo. But what we found that for de novo generation, when the model is trained on over a billion chemical strings, it does produce a lot of memorized strings from training data. So when we are looking at novelty, of course, we do take pleasure that it's generating a lot of unique and valid strings. But at a 30K generation size, we do see that about 68% of what it generates is memorization from training data. So I think this is, and that can be changed if we are changing the training set or the model parameter, and that's something we are exploring. And we do see that the novelty is something that do change the exact match. Or the exact memorization of the training set do change with the exposure to the training set. But the point I'm trying to make here that in the context of predictive model or in the context of generative model, as we are starting to build this scientific foundation model like Mole-Former, trained on broad scale data from public databases, likely that one factor that plays a role there is strong memorization. It can be used in good way and it can be used in bad way, as we have seen for the natural language models, but the story remains the same. How much time do I have?
Another 7 minutes.
Okay, good. Okay. So with that, I'll switch gear and I'll now get to the second part of the story, which has nothing to do with molecule, a spoiler. So here, as I mentioned, that I will be telling you about a new architecture that we are bringing into play for having better test time control of language model decoder. And we call this Larimar. Larimar is a stone, maybe you know, that has some implication with memory. But this is actually a set of class of generative LLM architectures with adaptive memory. And the paper we have just submitted the paper in arXiv, and the work is under review. The inspiration here comes from memory mechanism in brain in a loose sense, because in brain there is more than one memory mechanism. There is working memory, episodic memory, which is more short term, and then there is longer term semantic memory. But the point is that these different memory mechanisms in brain, they are all in play and they interact with each other, and that allows to happen memory consolidation and generalization and lifelong learning and so on and so forth. So we take this motivation in a loose way. And the other point here is that this different memory mechanism, they learn at a different scale. Episodic memory, for example, that happens in hippocampus is a fast learning mechanism. On the other hand, the neocortex, where the long-term or semantic memory learning happens, that's a more slow learning mechanism. So there seems to be this interplay and autonomous interaction between these different memory mechanisms, and that they can help each other to learn better and to generalize better. So we wanted to borrow this inspiration and see that if it is indeed the case that the decoder parameter of a language model does have all the memory of the training data, and we want to correct it or have a better control of it during test time, then does it make sense to add an external memory module which would be much faster learning compared to updating the decoder parameters, but it would influence the decoder during generation. So that is the whole goal of creating this Larimar architecture. So how do we do it? We have an encoder, a sentence encoder, and we have a sentence decoder, and we stitch these two using a memory module. Now, the memory module here is inspired from associative memory, but which is also distributed in nature. So this is not slot-based. And we train these 3 modules end-to-end. So the encoder, the memory module, and the decoder. And the memory module is a matrix that we are learning the parameter of. And we are also learning the addresses or the keys to map certain facts into this memory. And I call this episodic because during training or during test, this training or test happens as a new episode of data samples come in. So the model, the memory is updated with respect to this new data episode. We learn also how to map or how to address this new episode that just came in, and the episode here is a collection of sentences. And then we know that how to update the memory and the addresses for this particular episode. And during training, we enforce that by learning to query the memory, take the readout of it, pass it to the decoder, and the loss that we are learning on is the regular, the cross-entropy loss. But now it is conditioned on this W, which is the addresses that we have learned, and the parameters of M. So that is how it is different from if we are just doing a next token prediction loss, which is only conditioned on the previous token. Here, that loss is also now conditioned on W and M, that is the addresses and the memory. And once the training is done, now we can test it, but because we want to have a fast memory update mechanism, we don't do any forward passes or any back propagation to the decoder. What we do during test is that we update the memory by finding least square solution to a linear system. So that's much faster. That's just solving some optimization equation or linear algebraic equation. And once updated, this fast learning memory is then used to condition the slow learning decoder. And I will show you some results that how it works in practice. And in a sense that this actually now adds a state because LLMs, they are stateless, right? And now this, by adding this external memory module and conditioning the decoder output on this memory allows us to add a memory state to an LLM, which now we can use as a space-time controller. We show the performance of this approach on knowledge editing benchmark. So knowledge editing is a particular task where you have to update some knowledge, some fact that is in model's memory, and there are many different ways to do it. You can fine-tune your model on this new data or new facts that you want the model to learn on. You can find where those facts are in the decoder parameter and update only those parameters. Or you can just dump a number of facts in the context of language model and ask the model to follow those as it is producing the generation. What I'm showing you here, and so the one example is that if you ask a language model which has not been updated that who is the president of US, it will answer Trump. If it is old, has old and outdated knowledge. But if you want to ensure it gives you the right answer during test, can you do a quick fix that so it will output Joe Biden and not Donald Trump? And we want to make it fast and simple and efficient, right? So some of the methods that are state-of-the-art for model editing, they require, like I mentioned, updating the parameter and knowing which parameter to update. And when you look at their time, they take much longer to do, let's say, 10 edits. That's the number we are showing. And they are also they cannot handle, fact forgetting. Some of them can do sequential editing, or some of them can only do batch, and there is no one size that fits for all of this issue. And that was one of the tasks which we subject Larimer to, because if we really can update the knowledge of the model during test time and ensure that updated knowledge is reflected in its generation. So here are some of the results. The big table shows us the performance on a knowledge editing benchmark. The data set here is counterfact. And the 3 columns, big columns, edit success, paraphrase, and neighborhood. Edit success, of course, how accurately you are reflecting updated knowledge. Paraphrase is about generalization, that if you are querying the model with a rephrase of your original fact, can you still retrieve the correct answer? And neighborhood is about specificity. You should not degrade the model's answer elsewhere. Those answers should be unaffected. And with the advantage that we had, that the Larimer works at a much faster speed, you can also see it consistently performs across these 3 dimensions, that it does show good edit accuracy, good rephrasing or generalization, as well as specificity. Further, we also subject it to a forgetting task, where we write something in the memory that it should not output in generation. And then we also check that how robust this mechanism is by subjecting it to some rephrasing attack. So the success rate on the left table, lower the better. And you could see that Larimer, when it's asked to forget by this one-shot memory updating mechanism, it does forget and it does not output the forgotten knowledge in its generation at a much better capacity than other existing editing methods. So with that, I would say that I have two takeaways for myself and also for you here, that scientific foundation models can be prone to data memorization, which can benefit in task adaptation, as we believe has happened for Wolframer, while can also pose certain risks. So we need to really have a better understanding of what it has memorized and what it has not. And once we are there, once we know that memorization, training data memorization is crucial to all of these models' success, we need to also engage in developing more powerful and more knowledgeable scientific foundation model that we can control. And for that, I think the external memory-based control to decoder is an effective and efficient way of controlling the large language model, and which will enable us to ensure trust and safety in test time or when it is deployed. And last but not the least, the wonderful set of people I get to work at IBM and all my outstanding collaboration. I'd like to call out Jared, Vigil, Sam, and several others who has contributed to and actually has driven the Wolframer work. For Larimer, Shubhajit, Elliot, Igor, these are the people who have been driving that work. And collaboration I have with Yoshua Bengio's team and his colleagues at University of Montreal, MIT, Oxford, Rice University, and National Labs. And with that, I would like to thank you for your attention, and we'll take any questions.
Thank you very much.
Hi. Hi, Per. This is a really great line of work. So I'm from Professor Viswanathan's group. So we have been working on scaling up the molecular and materials foundation model. So I have two kind of follow-up questions of your GP, the Wolframer model. So the first one is that, so from the original Wolframer work to the GP Wolframer work, I think one smooth transition is that can you still do molecular property prediction, right? So can you do, now you're doing this GPT types of reconstruction or generation instead of the BERT type of thing, right? So do you think you can still do property prediction, but maybe in this autoregressive way, would this be better or worse than the BERT type of?
I don't know if it will be better or worse. We haven't tested, but there is some line of work, does not involve me, but it's called regressive transformer, where you add a token, to predict the property, and that seems to work well. There is also some work, not on molecule, but I just found out for large language model that you can use them as an encoder. If you just switch the string, rather than going from left to right, if you do left to right plus right to left, the last layer of decoder turns into an encoder, which you can use then as a property prediction, right? So these are all possibility. For GP Wolframer, which I didn't show, that we did come up with property guided generation and where it holds well. So it's more of an inverse design, not the forward prediction task. But it wouldn't have happened, and we came up with parameter efficient tuning of GP Wolframer. But the point is, if it was not general enough, it wouldn't learn this property to molecule mapping, right? So that's something we have already subjected it to.
It sounds like it's not quite clear whether this autoregressive or bidirectional encoding way.
All I'm saying that you can, if that's your objective, it will require work, but I'm positive that it will happen. And there has been, some past instances, not in the context of GP Wolframer, like in a transformer where you can train the transformer to predict the property token. Right now, we are just predicting the next token has to be a part of a smiles, right? But if you predict it like smiles and the next token and the property token, then it will learn to predict that.
I see. That's very interesting. And the separate question is, so now you're doing this molecular generation, and you're trying to scale this up to billion molecules as well. And you found, and the results looks like this novelty is pretty limited. Compared with maybe conventional ways that we do, right? A lot of the benchmarks have proposed validity, all those scores are very high. So what do you think the kind of the advantages that the scaling up is the training data set for generation task, compared to those previous models training on maybe 2 million molecules?
Generality of the generated molecules, right? Because when you are reporting novelty, and I hope I'll share the preprint with you. What we have looked into that novelty and all of this is also a function of the size of the pool that you are looking into, right? So, and also for all of those models, they estimate novelty for 30K or 10K generation, right? If you increase that number, your novelty will start to go down, right? So it is more of a test of scaling on the generation side. If you keep generating, do you still generate novel molecules? And that's some of that, I didn't mention, but even at a 10 billion generation, GP Mol Pharma still generates significant fraction of novel molecules. So that's one aspect, right? And the other aspect is that what your generations are novel respect to. If you are taking a small, let's say 250K to 1 million training size, yeah, it is novel to that, right? And here we are taking that up to the scale of 1.1 billion. So now it is novel with respect to that. So there is a natural trade-off, right? Small training set, big novelty, big training set, that. I think that's natural.
All right, one quick thing. It's break time, but we still want to continue the discussion. So people who want to go get coffee and snacks and everything can go to the assembly hall, and we can still continue the discussion in the meantime.
All right, Payal, beautiful work. So I was actually reminded in the Latimer work, Danny Kahneman's book of Thinking Fast and Slow, right?
Yeah,
I think this is a beautiful way of system 1 and system 2.
Yes, yeah.
Yeah.
I would say it's still far from that. It's inspired by that loose notion, but system 2 should be able to do much more than just remembering what I added in its memory, right? We need to get there. But yeah, thank you. Thank you for bringing it up.
Your question, please.
Oh, sure, yeah.
I have a question. Here.
Oh.
Yeah, so about the first section of your work, you said when increasing the training data set, the performance seems to be, there's an improvement there. And then you're saying then that shows how memory works. Why are you saying that the model is actually memorizing the data set instead of when you're increasing the size of the data set, it's actually increasing the coverage of the data set? That's how you improve the performance.
I think that's another way to, when we talk about memorization, it's not just, memorization about the particular string, right? I think that's more we show for GP Mol Pharma that, yeah, it is actually remembering particular string, right? But for property prediction, all what I'm trying to say that, the coverage is another way of memorizing, right? Yeah, you are covering the data set, but if the model is learning about what it's supposed to cover, then that is what it is helping it to predict the property. Right, if we just, go, I think, a few slides back here.
Yeah.
Yeah.
Thank you very much.
Thank you,
Yeah.
thank you.